Hello, I'm Ralph Gable of the Electronics for the Inquisitive Experimenter YouTube channel. So you bought a nanoVNA and kind of feel, well, a bit overwhelmed by the whole thing. Well, there are two aspects of this. First of all, with the whole idea of what is a VNA and, well, what can it do for you? Well, I have a whole series of videos that walks through all of the basics. And there's a link up in the corner and down in the description to the first video in that series just for you. The second aspect of this is just the whole thing of, well, the menus, the screens, and, well, in general, how to navigate this thing to set up for the measurement that you intend to make. And that is exactly what this video series is all about. In this video, I'm going to walk through the menu system from a very practical, well, what they mean to you perspective, centering on setting up for a measurement. The menu map for the nanoVNA may be found in the manual available at the link provided in the description. The nanoVNA that I will be using is a nanoVNA V2+4 with firmware version 20211227. And I just checked a little bit ago, that's the latest version. If you have questions or comments, please feel free to add a comment to this video. If you find this video helpful, please click on the like and don't forget to subscribe. So let's start with a high-level look at the top level of the menu system. So we turn on the nanoVNA and we see all sorts of colored stuff on the screen. Now, we're going to ignore all of that for now. We tap on the screen and the top level or main menu appears on the right. Let's take a look at each of these. Starting from the top, we see Display. This is where we go to set up what we see on the screen. Marker is where we set up markers that we can move across the screen once a measurement is made. We move a marker to a frequency of interest and the nanoVNA will display the value of the measurement at that frequency. Stimulus is where we go to set up the various aspects of the signal that the nanoVNA uses in its measurement. Calibrate is where we go through the calibration process to prepare to make a measurement. It is also where we go to save calibration and set up data. Recall is where we go to use previously saved calibration and configuration data to set up our measurement environment. And config is where we go to calibrate the touchscreen, see what version we're working with, and, well, other system level operations. Pause sweep is a checkbox. The default is to continuously sweep the configured frequencies. Now, there may be times when you want to pause everything while you do some setup or something. This is the place to do that. You tap to pause, tap to resume sweeping. Now, at the most basic level, the main menu items of greatest interest are going to be Display, Stimulus, Calibrate, and Markers. The easiest way to help you understand how all of this works is to walk through getting ready to make a measurement of some kind. So, what do we do first? Well, like anything that we do in the shop, the first step is knowing what it is that we're trying to accomplish. Not just in generic, ethereal terms, but a real plan in mind. With the nanoVNA, we want to ask questions like, what am I trying to measure? Am I trying to measure SWR, impedance, insertion loss, gain? What? What is the frequency range that I want to measure this in? Am I interested in a particular range of frequencies, such as the extent of a particular frequency band? Am I interested in a specific frequency and a range of frequencies around that specific frequency? What sorts of cables and or adapters am I going to need to interface with the thing I'm testing? And how and where am I going to connect my calibration standards? Now, let's just say that we have all this laid out. We've got a plan. Now what? Well, the next step is actually up to you. You could configure your nanoVNA to display what you're looking to see first, or you could configure your nanoVNA's frequency ranges and the like to cover the frequencies you're interested in. For this video, I'm going to configure what I see on the screen first. I tap on the screen to bring up the main menu. At the top of this menu is the display entry. I tap on this to bring up the display options. At the top of the display menu is the trace option. This is where we go first to enable and disable traces. But more than that, it is where we go to select the trace we are going to configure for our measurement. So what sorts of things can we configure for a particular trace? Well, what sort of measurements we're making, how are we going to display the results of those measurements, are we going to be averaging a number of measurements together and the result of that average be displayed, and well, a whole lot more. So let's begin by tapping on this menu item. You have up to 4 color-coded traces displayed on the nanoVNA screen at any one time. Each of these traces can represent a different measurement or all the same measurement configured differently for each trace. But you do not have to have all 4 traces visible all the time. You can shut off traces that you do not need. We can see all 4 traces in the trace menu on the right. All 4 are enabled at startup by default. You can disable any one of these traces by double tapping on the selection in the trace menu. The colored menu item grays out when the trace is disabled. Once you have disabled all of the traces that you will not be needing, we can proceed to configuring the trace or traces that we will be using. We start this process by tapping on the trace entry in the trace menu to select that trace. Now we tap on the back menu item to return to the display menu to continue our configuration. Well, the next step is to configure the format of the trace, which to some degree also determines the type of measurement being made. Now there are 2 aspects to this. The first is the channel that the measurement is going to be made on. Now, there are 2 channels. On other VNAs, these are referred to as port 1 and port 2. On the nanoVNA, these same ports are referred to as channel 0 and channel 1, respectively. The second is the type of display you want to see. This determines a lot about the actual measurement you're making, but it is also about what you're trying to do, too. There are different ways of displaying the same data depending on the thing you're trying to accomplish. So let's look at channel selection first. We are currently at the display menu. On this menu, you will find the channel option. Tap on this menu entry. Now we see 2 entries in the channel menu. We see channel 0, reflect, and channel 1, through. Channel 0 is exclusively used to measure things like SWR and impedance on the nanoVNA. These are all of the reflective measurements. That means that the VNA sends out a signal to the device under test and then looks at the signal that returns to make the measurement. Channel 1 is used exclusively to measure things like insertion loss, frequency response, delay, well, through type measurements. At this point, you tap on the channel that will be involved in the measurement you intend to make with the selected trace. Well, so much of what the display formats are all about is centered around what is called the reflection coefficient. So, if you're going to have some understanding of what these things are, I need to spend just a moment explaining what this is. First, all of the reflective measurements that the VNA does start with the reflection coefficient. This is what the VNA measures and then mathematically calculates everything else from that. The reflection coefficient is a complex entity. That means that it is comprised of both a real and imaginary part, just like impedance. It is represented by the uppercase Greek letter gamma. The magnitude of the reflection coefficient is found by the square root of the real part squared plus the imaginary part squared. The phase of the reflection coefficient is found by the inverse tangent of the imaginary part divided by the real part. I've provided a go along with the video sheet with all of the equations for you. You'll find a link to this downloadable sheet in the description. Another thing that you're going to be hearing a lot about is normalized values. It is a way of measuring one thing relative to another without regard to an absolute value of either thing. So, if I'm using a 0.2315 volt signal as my source signal, and I'm looking at the other end of a cable and getting a 0.201 volt output, the normalized output signal would be, well, signal out divided by signal reference, which would be equal to 0.201 divided by 0.2315, so the normalized output voltage level is 0.868. With this very brief explanation under our belt, we can get on with looking at the various display formats. At the top of the list is log magnitude. In reflective mode, in other words, using channel 0, this is the return loss expressed in dB. 0 dB return loss means that all of the signal being sent to the device under test is being reflected back at the VNA. The more negative the number, the less signal is being returned to the VNA. In through mode, also known as using channel 1, this is the insertion loss or gain expressed in dB. It tells us how much of the signal that is being sent out of channel 0, in other words port 1, is getting to channel 1, also known as port 2. It is negative if we're losing signal, which is typical for insertion loss. The more negative the number, the less signal is getting through. It is positive if we're getting more signal into channel 1 than is being sent out channel 0. This is typical for an active device under test like an amplifier. The higher the positive number, the greater the gain. Now, on to the next option. Well, the next option that we have is phase. In reflective mode, this is the phase of the reflection coefficient as described previously. In through mode, this is the phase of the signal coming into channel 1 relative to channel 0. 0 degrees means that they are in phase. The next option, though, is a real puzzler. Well, the next option on this menu is delay. Well, what is this whole delay business? Now, we're used to thinking about things like the propagation delay through a digital logic gate. In other words, the time it takes for an input logic change to be seen at the output of a gate. But now we're in the frequency domain of the VNA. Now, right out of the gate, it doesn't have a lot of meaning in the reflective realm. However, it has a lot of meaning in the through measurements. Now, without going into the calculus behind it, think of this as the rate of change in the phase of a signal as the frequency of that signal is changing. You can kind of think of this like the velocity of a car as seen in the time domain. Bottom line, it helps predict if we're going to experience phase distortion as a signal passes through the device under test. We want this to be as flat a line through the operating frequency of the device as possible. In other words, we don't want our car to be accelerating or decelerating. Just put it on cruise control. So how is this related to the term delay? Well, phase shift is descriptive of a time-related change. If one frequency signal is shifted in phase more than another, this means that the time at which the signal is passing through 0 degrees is going to be different. Thus, delay, a time-related entity. Now, on to the next option. Well, the next option is the Smith option. What you see here depends on how you set up your markers. To access the format options for the values shown on the Smith chart, you have to go all the way back to the main menu, then tap on the Markers option, and then the Smith Values option. In reflective mode, the Smith format is where we go to measure the impedance of a given device under test. By default, the nanoVNA displays the impedance as resistance plus capacitance or inductance when a marker is defined. You can also display this in terms of the reflection coefficient in both the linear and log marker format. In the linear format, we get the normalized magnitude and phase of the reflection coefficient. In the log format, the magnitude is expressed in terms of the return loss in dB. With the marker Smith values in the format of RE plus IM, we see the reflection coefficient in all of its glory. Then we have the R plus XJ format, which is resistance plus reactance display. And then finally we have the R plus L slash C, which is resistance plus capacitance slash inductance. In this mode, the nanoVNA translates the reactance into capacitance or inductance values at the frequency where the marker is sitting. If the reactance is negative, it gives you capacitance. If it is positive, it reports an inductance value. In the through mode, this can show us a few things depending upon the format you choose when setting up your markers. It can show us the magnitude and phase of the signal exiting the device under test in both the linear and the log marker data format options. In the linear format, the magnitude is expressed as a normalized value relative to the signal level being sent out from channel 0. The same is true of log format, except it is expressed in dB. The equivalent transmission line impedance modification as we move along the transmission line from channel 1, the load, toward channel 0, the generator, clockwise around the Smith chart. It is in this direction because this is the value as viewed from channel 1, the load's perspective. This can be expressed in terms of normalized polar coordinates, resistance plus reactance, or resistance plus capacitance slash inductance. We now look at a very familiar format. Well, the next option is SWR, a very familiar format. In reflection mode, this is the voltage standing wave ratio. Yes, it is calculated from the reflection coefficient. You can see the go along with the video sheet for that formula if you're interested. Now, SWR has no relevance in through mode. Next, we have to go to the More menu item for the rest. We tap on the More menu item of the Format menu. At the top of the list is the Polar item. Well, what does this mean? Well, in reflective mode, this is where we get a real view of the reflection coefficient. The horizontal axis is the real portion of the reflection coefficient, and the vertical axis is the imaginary portion. These are normalized values. The angle that the resulting vector makes to the positive horizontal axis for any given point is the phase of the reflection coefficient at that frequency. The length of that vector is the magnitude. In through mode, this is showing us the through response in terms of normalized values. Now, what this means is that the values you see here are relative to the incident signal coming from channel 0. A value of 1 plus 0j means that we're getting the exact same signal into channel 1 or port 2 that is being sent out channel 0 or port 1. The angle that the resulting vector makes to the positive horizontal axis for any given point is the phase of the signal relative to the signal from channel 0 at the given frequency. The length of that vector is the magnitude of the signal relative to the signal from channel 0. In the case of a filter or other passive device, the magnitude will never be greater than 1. In the case of an active device like an amplifier, the magnitude may be greater than 1. Now, we go on to some related formats. Well, the next format is linear. Now, I just talked about the polar format and referred to the magnitude and phase of the vector for any given point. The linear format represents that magnitude. In the case of the reflective mode, this is the magnitude of the reflection coefficient. In the case of the through mode, this is the magnitude of the signal that channel 1 sees. Again, this is a normalized value. If it is 1, then we're getting the same signal amplitude into channel 1 that is being sent out of channel 0. The next option is also related to the polar format. Well, the next option on our list is the real option. This is the real portion of the complex value provided with the polar format. In the reflective mode, this is the real portion of the reflection coefficient. In the through mode, this is the normalized real portion of the measure of the signal coming into channel 1. Now, as you probably might guess, there's one more option directly related to the polar values. Well, the last of the options that is directly related to the values provided with the polar display option is the IMAG option. This is short for imaginary. In the reflective mode, this is the imaginary portion of the reflection coefficient. In the through mode, this is the normalized imaginary portion of the measure of the signal coming into channel 1 from channel 0. The next two display options relate to impedance measurements only. Our next option relates back to the values provided in the Smith chart. It is the resistance or real portion of the impedance. It only has meaning in the reflective mode and totally ignores the reactive portion of the impedance. There's yet one more to go. Well, this last option also relates back to the values provided with the Smith chart. It is the reactance portion of the impedance. It too only has meaning in the reflective mode and totally ignores the resistive portion of the impedance. But there's one more entry to go. Well, if you're not familiar with what Q factor is, I have a nice video that will explain this in detail. There's a link up in the corner and down in the description to this video. It was amazing to me. The two manuals that I have for the nanoVNA do not even mention this option. So very quickly, there are two ways of calculating Q factor. In reflective mode, the Q factor of the device under test, as seen by channel 0, is the reactive part of its impedance divided by the resistive portion of its impedance. It is considered to be a measure of the quality of a component like a capacitor or inductor. Now, in the past, I have not been totally enamored with the consistency of what I've seen with this myself, so I don't give huge amounts of confidence in this measurement by the nanoVNA. Now in through mode, I'm also not convinced that it does this one properly for a filter or other similar application. For instance, the Q of a band pass or band reject filter is determined by the center frequency of the filter divided by the bandwidth of that filter. And I have very similar feelings about this aspect of the nanoVNA as I did with the reflective. Maybe it's just operator error. Maybe it's unreasonable expectations. I don't know. Anyway, next steps. You have to return to the trace menu, select the next trace to be configured, and repeat this process for each trace you need for your measurement. At this point, we have chosen our display format. We're ready to define the frequencies that we're going to be using for the test. Well, there are two basic ways of setting the frequency limits for our test. How you do it depends a lot on what you're trying to accomplish. The first is to set the start and stop frequencies. Now, this is useful for applications like measuring the SWR of an antenna, which operate between two known frequencies. Now, I have one very important note for you on this one. The start frequency must always be below the stop frequency. In fact, the nanoVNA won't let it to be otherwise. So why do I make a point of saying this? Well, suppose that you have just finished doing some measurements in the 7.0 to 7.3 megahertz frequency range, and now you want to do the same measurements in the 21.0 to 21.45 megahertz range. You cannot define the start frequency first because the existing stop frequency is 7.3 megahertz and the new start frequency is 21 megahertz, and it's definitely higher than the 7.3 megahertz. So you have to define the stop frequency first and then the start frequency. To do this, we have to be sure that we're all the way back at the main menu by tapping on the back menu item of each menu until we arrive. Then we tap on the stimulus menu item. Here in the stimulus menu, we see the start and stop menu items. I tap on the start menu item to set the start frequency. A pop-up keypad shows up. Using the numbered keypad, I enter the frequency either in kilohertz, megahertz, or gigahertz. I tap on the K for kilohertz, M for megahertz, G for gigahertz once I have entered the numbers. Done. I do a similar thing for setting the stop frequency. But there's a second way to do this. So suppose that I wanted to test a bandpass filter. I know the center frequency of the filter, and I know the frequencies either side of this that I want to see the response for. Now, in a case like this, I would specify the test frequencies using the center frequency and span method. We start by specifying the span. Now, the span is the total width of the measurement from what will become the start frequency to what will become the stop frequency. Now, this can be specified in kilohertz, megahertz, or gigahertz. Again, if we're starting from the main menu, I tap on the stimulus main menu item, then the span in the stimulus menu. We specify the width of the measurement window the same way we entered the start and stop frequencies in the pop-up keypad. Then I tap on the center menu item to specify the center frequency by the same method. Done. So what is a marker? Well, you can think about it as a pointer. You have a nice graph of values on a piece of paper, and you take your pencil and point to the spot on the graph, and the pencil says, "The value at 51 megahertz is 36.1 ohms. Thank you. That is what markers do for you. You can have up to 4 markers defined, and each marker will display its information in a format commensurate with the display format that you chose for the selected trace. Well, the first step in setting up your markers is very similar to what we did with setting up the display format. First, we have to go all the way back to the main menu. Then we tap on the marker menu item. Next, we tap on the select marker menu item. We can select and turn a marker on by tapping on its menu item. A check appears next to the markers that have been enabled. If I tap on a selected marker again, it turns it off. Its status will toggle each time I tap on it. If you want to disable a marker that is enabled but not selected, you first have to tap on its menu item to select it. a second tap will disable the marker. Now, the only formatting you can specify for the data displayed by a marker is with the Smith data as described earlier. Here you have to select the marker to modify, then tap back to get back to the marker menu. Now tap on the Smith value menu item and then select the data format you want for that marker when displaying Smith chart values. Repeat this process for each marker you choose to use. Then tap in the middle of the screen to dismiss all menus. So how do you use the markers? You will notice that a marker appears on every trace that you have configured. To see the data associated with a particular marker on a particular trace, just tap on it. The data associated with it is displayed at the top. To move a marker, tap and drag the marker along the trace just like you are drawing the line that is the trace. Once you leave the trace, the marker will stop moving. You can search for maximums and minimums easily, even track on a maximum or minimum. We begin this process by tapping on the specific marker on the specific trace of interest. Now I tap on the screen to bring up the main menu. Then tap on the marker menu. Finally, tap on the search menu item. Here you can see that you can choose to find a minimum or a maximum by tapping on one of these options and then enabling tracking by tapping on the tracking option. This marker will now follow the peak or valley found. This is great if you're trying to tune a filter or antenna. As you change the tuning, the marker will follow your progress, reporting the measured value. Now we're ready to begin the final preparations for our measurement, calibration. Well, the key to remember when doing the calibration is that we only want to include the device we're testing in the actual measurement. Any addition of cables or adapters between the device under test and the VNA after calibration changes this. We want to include every cable and every adapter we use in the calibration process. For reflection measurements, you'll need a short, open, and load calibration standard. For through measurements, you will need a short, open, load, and through calibration standard. Sometimes you'll have to add or remove an adapter after calibration in order to connect to the device under test. Well, this is covered through the use of a port extension. In the nanoVNA world, this is referred to as electrical delay. One more really cool thing. At the end of the calibration process, you tap on the Done menu item. You will now have the opportunity to save the calibration data you just completed. But more than that, it saves the entire measurement setup, including trace definitions and scales and marker definitions, and, well, a whole lot more. To come back to this same place, all you have to do is recall the specific configuration you saved. The recall option is available on the main menu. You will be able to see this process of calibration in the next videos of this series. I will set up, calibrate, and measure some common things that the average experimenter might be interested in measuring. These will include the SWR of an antenna, the input impedance of a filter, the frequency response of a filter, maybe the gain of an amplifier, maybe some other things. I already have a video which talks about how to measure impedance, capacitance, and inductance using the nanoVNA. The link is up in the corner and in the description for you. In this video, I used the nanoVNA in conjunction with a computer. I also have a video on how to measure things that exist outside of the 50 ohm world of the nanoVNA. The most common is the 75 ohm world, but there are a lot more than that. A link to that video is found in the description if you happen to be interested. Well, in the next video, I will set up a nanoVNA to measure the SWR of an antenna intended for use in the 7.0 to 7.3 megahertz amateur radio band. Included in that video will be the complete setup, calibration, and measurement process. Well, you know, there's a lot more exploring to be had with your nanoVNA. My hopes are that this video has, well, maybe rolled back some of the fog that was there. If you found this video helpful, please click on the like and subscribe to the channel. Thank you so much for watching. Until next time, Toodle-oots!